proportional to the concentration of whatever it is it's doing. So here I've written this out as A equals A star. So I took it to you in the last part of the lecture. This part of the concentration or mass or chlorophyll or turbine or whatever volume times the concentration of that. I think in your lab handout this afternoon there's going to be a little bit of appendix that is for a capital A equals epsilon times C. That version from chemistry class will relate to. I'm not going to muddy the waters here. If there's multiple absorbing substances, as we know that there are, you can actually model that as a sum of all of the constituent absorptions. So that's our Beer-Bourgeois law. So we can derive this, which I'll walk you through here, for a theoretical volume of water, right? Where we've got, so this is the diagram on the left-hand side. So the gray shaded box is our theoretical volume with some absorbing and scattering substance in it. And we've got our radiance that's coming in. We've got the path length over which the light's interacting with whatever's in our volume. And then we've got radiance that's been absorbed, the radiance that's transmitted through without scattering, it just isn't absorbed or scattered, and then the radiance as a function of angle that gets scattered within that volume. And this is a function of angle. You have to integrate that in all directions to fully account for those are your concentrations. Light that comes in is equal to the light that's absorbed plus the light that's scattered plus the light that's transmitted. And you're going to get into the scattering bit. Wayne's gone, but that's going to be wrong. Okay, oops, and I drew all over it, but assume that there is no scattering for now, for simplicity's sake. So I just covered up. Somehow I covered up the gray box too. No. Did you guys ever see the gray box? The gray box has always been gone. Problem. Hang on. Sorry, my iPad's giving me. Take that out. And I'm just going to draw. I'm really sorry about that. I don't know why. I guess we know that light shaded things don't show up in this projector. That's the gray box. It's not gray here. Now you can see it. Really sorry about that. Feel free to just shout at me. What gray box? If I say that. So this is our hypothetical volume, the absorbing scatter. So, okay. So we're assuming no scattering. So now the light that's absorbed is equal to the light that came in minus the light that's transmitted. Okay. And I'm going to draw the box again. Okay. So we can define the absorption coefficient as the fractional loss per unit distance light through that volume. So A, and then on the top we've got the fractional, this term here inside the parentheses, fractional radiance loss. So incident minus transmitted, the absorbed part, right, divided by the incident. So that's the fraction that got lost. It's negative because we're losing it, and it's in this delta R, in that path length. And we can simplify that then to just say we're looking at the change in the fractional radiance for change in wavelength. All right, so now we can rearrange it. We can collect our terms one and the other. We've got the absorption coefficient as a function of the path length. Absorption is constant. We're assuming it's constant through that. Like it's a well-mixed little hypothetical volume, right? So it's a constant. Then we've got our change in fractional radiance that is a function of distance, right? And that's what we're going to. And now we can integrate both sides. We're going to integrate them both over this path length R from 0 to R. A is a constant, right? So that goes outside. And then we have to integrate 1 over radians as well, which is, I'm not gonna make you guys, that's the integral of 1 over x. But we've got the, box. So now we've got, if we integrate this, so a is a constant, it comes out. So on the left-hand side, we've just got a times r minus 0, our definite integral. And then on the right-hand side, we've got our negative sign still, and then the integral of 1 over p is log of that, right? And we plug in our limits of integration as well. So the different term. Now, we can simplify the left-hand side, and we can substitute the actual radiance values on the right-hand side. So we know that the radiance in r is 0, initial point, radiance in r, transmitted. Okay, so we substitute those in, and then solve for a. We come out with this: the absorption coefficient, the log negative of the log of the light that comes out divided by the light that went in, all over the path length r. And we can rearrange that to give us this, which is equivalent to the thing with L that I showed you on the second slide. Okay, so we've just gone through and set up our hypothetical volume and derived the exponential decay. So this is what Lambert did, I believe. He actually came up with this mathematical expression for the exponential. Okay, what should the units be? Just based on the equation. If you look at this equation, per meter, right? So R has units of meters, and this is unitless. Okay, so absorption coefficient has units of inverse meters. So one of the first instruments that you guys are going to learn how to use in lab this afternoon is a spectrophotometer, benchtop instrument that measures the difference of light through a ball. How many of you guys have used a spectrophotometer? Okay, about half the class. So some of you have got some familiarity with this, some of you don't. So we'll go through it all. But spectrophotometers often will report absorption, or sorry, absorbance rather than absorption. So this is the definition of absorbance. Couple of key differences. One is that it's log 10 instead of natural log. That's just chemists like their log 10. Optical oceanographers like natural log. Fine. You know how to deal with that. And there's no path length, right? They're not dividing by r. So the units of absorbance, there aren't any, right? It's unitless. Okay, so if we want to convert, we need to first change our base. After log 10 is 2.303, and then you divide by the pound. So absorption equals 2.303 times absorbance divided by the pound. I put a footnote down here that sometimes in some papers you will see A called, big A, absorbance called the optical density. They are equivalent. And I think I will show you some figures in this lecture, and you will see them throughout your reading and everything, where it's one or the other, and just note it. Good? All right. Gray box. So that was the sort of theoretical definition of Pierce's law with no scattering in our volume. But of course, we always have scattering to some degree. So what gives? We want to measure real water with real instruments. So option one, well, we could filter these scatterers from the sample. If you are interested in CDOM, or if you're doing this afternoon's lab, that is what we will do. So just don't deal with it. Option two is you can come up with a sensor that collects almost all the light that's scattered, and then measures a fraction of that can be used for normalized. Okay? So we can integrate all that scattering and have a device that actually measures the light that goes in all directions, and then you can determine scattering or the absorption by difference. Or our third option is to use a method that collects none or some or nearly all of the scattered light and makes some well-justified assumptions about that scattering. And then it turns out that practically there are some methods that land here. I mean, there's always option one, right? But if you want to measure the particles, then there's some handful of methods that do this, and a number of methods that do this. We're going to do a little bit of both in lab and okay. So option one, we filter the water. There is no scatter. We can just use a benchtop spectrophotometer in this case. So this is one of the sort of oldest ways of doing this. So basically you take a sample and you put it inside a cuvette, which is a little oblong, rectangular, of various sizes, quartz or glass or occasionally polystyrene, depending on what you're doing, but a transparent container that fits into, black color is not the right one, fits into one of the sample holders in this. This is the instrument diagram from Shimadzu, a double beam spectrophotometer. So you put your sample in here, and there's a light source over here, generated, it's split into its wavelengths. It is a complicated set of mirrors and gratings and things pass through both the sample, so the light comes in this way, and through a second simultaneous cuvette for reference. Light gets split, goes through both at the same time, and then gets collected by a detector. Okay, so this is the guts of how the spectrum comes. So we need to measure the transmitted light by both the sample and the reference. What should the reference be? You've got seawater in your front. See that? What goes in the back? Nothing? Millicue? Okay, we could put fresh water in there. What should we put it in? In cuvette, hopefully a cuvette that is as close to the front cuvette as you can, right? So you don't have a lot of differences between the two, although you'll zero against both. Okay, so matched cuvettes, reference, millicue is a good reference. You are thinking about salinity differences, or you're measuring in a spectral region where it's not that important, right? But it's always important to think about what goes in the reference. In some applications, maybe you want to make a reference that has the same salinity, millicube of sodium chloride or something, as your sample. Right? So there's things you can think about when you're choosing what should your reference. Okay, then you can compute the sample absorbance by difference relative to the reference. So if we're interested in the absorption or absorbance of a filtered seawater sample relative to pure water, and take out the influence of pure water, then we can subtract one from the other, which is equivalent to minus log 10 of the transmitted light through the sample divided by the transmitted light. Back up a couple of slides, you can find the absorbance definition and work out how that works. Okay. Oh, and I didn't say on here, there are spectrophotometers out there. This is a double beam spectrophotometer where there's a reference and a sample always being measured simultaneously. There are also single beam spectrophotometers that get used for certain applications, particularly if you need a special cuvette holder or you need just stick a filter pad in the path or whatever, where you don't necessarily have a reference in the same position. And then you have to measure your reference, take it out, measure your sample, take it out, and hope that your lamp isn't drifting or anything in between, right? So there's simpler single beam. Okay. So remember that we've got this path length dependence for absorption in the formula. For absorbance doesn't have R in there. So how will the spectrophotometer's measured absorbance change path length gets longer. You have a light path through the sample to go through 10 centimeters through the sample instead of 1 centimeter through the sample. How would the absorbance change? Absorbance, yeah, just the raw thing that comes out of the spectrophotometer. Doesn't change. So if we have sample and light comes in, or if we have a sample and light comes in, this one is going to have more light coming out the other side. Okay, so if R is smaller, then this is going to be larger. It means that the ratio in the parentheses is going to be larger. You find it's log 10 is smaller, right? So if you have a short path length, you will have lower absorption. Increase your path length, you'll have higher absorption. This is an annoyance about spectrophotometers. Not really. You just have to do the correction yourself. But this is important to keep in mind. So you have different path length cuvettes. This is a schematic from do again, I think, showing all the things you can buy to change the path length of your sample. And the goal is to have absorbance always falling between about 0.1 and 0.4. If you have absorbance really low, then you're going to have really small differences, right? The transmitted light, you're going to have a lot of transmitted light coming out. And if you're trying to look at small changes, you might be difficult to resolve those. If you have absorbance really high, then you have not a lot of light coming out, and you're going to start to get more noise from your instrument. That detector is going to have fewer photons to detect. So we want to keep that absorbance in a range that's good for the instrument. And if that means we need to adjust the path length, then we will. Or in some situations, we might be able to use a sample, but that's not always. You want to play with the path length relative to the absorbance of your sample, so you're getting a good read for the instrument. And if you think about CDOM, really high absorbance in the blue and UV and low absorbance in red, the path length that you need might actually be different for different parts of the spectrum. No, good. Okay. All right. Sometimes you might have a really tiny, small volume sample, or one that is absorbing very little, but you still want to characterize its absorbance or its absorption coefficient precisely, in which case you need a really long path, right? Those cuvettes that fit inside spectrophotometers typically max out at 10 centimeters. You might want more distance than that. And so for some applications, people will use something called a liquid core waveguide, or sometimes it's called a liquid waveguide capillary cell, but it's basically a tube, hollow tubes with quartz or Teflon coated walls that are really reflective. So you run your sample through the tube and light comes into the walls of the tube and then bounces around down the length of the tube and then out again to a detector. And you can characterize that bouncing to figure out what the effective path length of your tube is and determine the absorbance that way. So this is a cross section of what the tube looks like, and then this is what the actual instrument looks like. Input for liquid, an output for the liquid, and then an input for the optical fiber and an optical fiber that go over to a spectrophotometer. So these are really sensitive. They're kind of finicky. Very careful not to get calculate tiny particles, retained stuff from the previous sample. It could be kind of a beast to work with, but they do allow us to measure absorbance or absorption directly for instance, open ocean CDOM, right, where it's very low, and we want to get that. There's a good, if you're interested in this method, Sherry Floyd in 2009, where she really exhaustively described all the cleaning protocols that they used and the effects of microbubbles and things like that. This is another path length extension option that's out there. Okay, so imagine now that scattering is not negligible, we haven't filtered, or we actually want to know the total absorption, including the particles, or just the particles. Then we need to collect all of that scattered light. So this is the option 2 on the last slide. Here is the gray box. Okay, so now we've got scattering again. And what we're going to do in this option is to put our volume inside a sphere with an inside a reflective surface on the inside, almost as close to perfectly reflective across our wavelength region of interest as we can get. And this is called an integrating sphere. So it's integrating literally all the scattered light around it. And so the way that this works is you might have a port. This is an opening in the wall of the sphere. Oops, I put it in the wrong place. Draw better. Right there. Okay, so we've got our light that comes in from a light source outside. And then usually the detector is orthogonal to that, maybe under the sample. So I'm showing this to you on a 2-dimensional slide, but imagine in 3D, it's a sphere, right? So the bottom, on the bottom of the sphere, this dashed box here might be the detector. It's like underneath the sample. So the light comes in, some of the light gets absorbed, goes straight through the sample. What comes out comes straight through the sample, and then it's gonna bounce all over the sphere, blah, 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 all around until it's all integrated. And what the detector sees on the bottom, just a little bit, should be a known fraction of all the light that's going all the way around the sphere. So we should be able to, so any light that's lost was only lost because it went through the sample. Okay? What's the path line traveled by this light? We shoot it into a sphere, bounces all over the place. Kind of long, right? So this isn't actually the way we're going to do this. So we want to think about the path length just the sample. And to back out this bouncing around, we're also going to measure a reference, right? So we're going to have another port. We'll put it down here somewhere, maybe. I don't know. I'm doing my art really badly here at this point. But for our reference, and I better make it cool. So for reference, light will come in, but we'll shoot it in a way that it misses the sample on the first pass. And then it goes and it bounces all around. Same thing, and gets measured, right? So now the only difference between our reference and our sample is that the reference didn't pass through this pathway on the first entrance. Okay, this is ref and okay. So that's going to correct for the fact that the path length gets like way big. It's bouncing around inside the sphere. We're really still only looking at that level. So with both the sample and the reference, we don't have this. Okay, so then we're measuring the observed light as the difference between what's in and what's scattered and transmitted is what we measure. Okay? Measure that at the end of it. So there's a couple, there are ways to get, although I think it's difficult now. Actually, Colin and I were just talking about this yesterday. There's not too many commercial options for this anymore. You get an integrating sphere that attaches to a spectrophotometer, but you guys are going to get to work with one tomorrow afternoon. You can also buy now integrating spheres that are meant to either work on the bench top or go in the water. And they're what are called point source integrating cavity absorption meters. So a light source goes down into the cell or into the sphere, and actually the light goes all over the place, but the same principle is going. All the side, there's a couple of different manufacturers that make those now. Okay, so this is one way you can do it if you want to know about scattering things, and you can stick things other than fluid volumes inside. You can put a cuvette inside, and that's how the most careful measurements are made. We're not careful, they're all careful, but how the measurements against, we reference a lot of other methods against measurements where you put a volume of fluid inside the integrating sphere. You can also put filters inside an integrating sphere, right? You can put anything you want in there. So that is our integrating sphere option. Okay. Option 3 is to make some well-justified assumptions about the light that's lost to scattering and may only be partially detected. The integrating spheres are great. They're expensive. They're a little bit finicky to keep clean and take care of. So it's nice to have something that is seagoing a little bit more and can give you continuous measurements on the water. Or allow you to take a sample and partition it out into its different constituents. So one thing that often gets done, if you just want to know AP, so the absorption due to particles, is to filter your sample onto a filter and measure its geometric path lengths. And I talked about this in the morning, so for cool, I'll keep on going. So this is where we've got our geometric path length, which is now we're using L for this. Sorry about the switch from L to R and back to L. So if you have a filter that you collected your particles from your sample on and you know the volume, you can calculate the geometric path length. You can take that filter and you can put it, you can shine light through it and measure the absorbance, so the absorption across the filter. So there's a few different ways that it's done. One is just in transmittance mode, which is the one on the left-hand side here. So you shine a light through a glass fiber filter loaded up with particles. A lot of scattering, right? How many of you guys have seen a glass fiber filter before? About half the glass. I should have brought one in. It's white. It looks like a sponge, kind of, I guess. You look at it under the microscope. It scatters a lot of light, right? It's very diffuse, right? So if you shine a light through a glass fiber filter, the light's going to go in a lot of different directions. If you've got particles on there, some of it will be absorbed. So we can use a reference filter to try and back out what's just been scattered by the filter. We can also use an integrating sphere to help with this. So we can put in paired measurement, you put the filter at the entrance to the sphere, shine light through it, and collect the light that gets scattered out after the filter. And then you can put it at a port that's opposite the incoming light and measure the light that's reflected off the filter back into the integrating sphere. And using these two measurements in tandem, you can estimate the absorption by the filter. Again, you need a blank filter that's got same scattering properties, but not the particles. And then finally, we can put the filter in the middle of the sphere, exactly the way we did talking about with the water volume on the left. So that's the inside sphere IS. All right, and for all of these, you need to also measure and subtract the absorbance of a similarly moistened light filter. And you want to estimate the uncertainty of this, the noise. To estimate the uncertainty like scan. Okay, so simply subtracting the absorbance of the blank filter from the absorbance of the sample filter. Is that going to correct for any light that's scattered by the Okay, so there's light scattered by the particles on the filter, although the light scattered by the filter is much bigger, but yes. What else is going to go on? We have lots of scattering in the filter. The light's traveling a longer distance through that filter than it would if it were just traveling. It's just going to scatter by particles. So you take those particles and put them on a bright white, spongy looking glass fiber filter. It's going to bounce around a lot. So we're going to have path length amplification inside. We can't just subtract the absorbance of the blank. We also need to subtract a correction for that path length amplification. luckily, people like Colin and Daria Kennedy and some others have made careful absorption on filters paired with absorption by the same stuff in a volume in the center of the sphere, and empirically figured out what should this path length amplification correction be for this kind of filter for glass fiber. So the data that are shown in all of these panels are comparing the optical density, the absorbance by the filter in 3 different methods. So the P method is the one where we just shoot the light through the filter without an integrating sphere. The R method is where we have the filter alternately on the entrance and the reflective part of the sphere, and then IS is when it's in the middle. So we can compare all of those to the equivalent absorbance by the suspended volumes in the same position. So there's a lot more measurements with just the transmitted method because integrating spheres are expensive and not everybody has them. But there are several studies that are now showing this relationship amplification, right? So inside the sphere, there's the least curvature, right? Which kind of shows us that the inside the sphere is correcting for fewer things. But this function that I put on the slide here, it's also going to be in your lab handout. We're going to do this with the filter pads inside the sphere methods that we'll do tomorrow. You can correct your filter measurement to give the equivalent in suspension measurement. So that's just saying, okay, here's what it would have been. Okay, so we apply this empirical correction to remove that effect of extra bouncing around inside. Make sense? All right. Other way that we can make an absorbance or absorption measurement that doesn't quite collect all the scattered light, but we can correct for it, is using something called a reflecting tube absorption and attenuation meter, or AC meter. Wet Labs developed or commercialized this back in the 90s, and then Wet Labs got acquired by Seabird, so now Seabird sells the ACS. So there's an ACS, there's an AC9. The only difference is ACS is hyperspectral 4 nanometer or 4 nanometer resolution from 400 up to like 750. And the AC9 only has 9 wavelengths to it. The principle of the absorption meter, we have an instrument that has one path for measuring absorption, and basically it's like a cuvette, right? But it's a slow tube that your sample water goes through that has reflective walls. Like most of this type. And you have a silent or has absorbing platform. You're in a narrow field. One side you measure absorption, and on the other side you measure the beam attenuation, which we haven't talked about yet. So I'm going to give you just a little bit, and Emmanuel is going to do a very thorough job of it tomorrow. So the gray box. I probably don't need to draw the gray box anymore, do I? So down here we've got some schematics, mostly text about how these 2 different sides appear. So here's A, absorption. Here's C, beam attenuation. So in both cases, there's a source. The A side has the reflecting walls, and then the detector has a diffuser in front of it. So it's looking in all directions, trying to collect all the light coming in, regardless of coming straight through or being bounced off. The C side, the attenuation side, does not have reflective walls. So anything that gets scattered into the walls should be absorbed and not be detected. And then there's a detector in narrow field of view that should exclude the scattered light, right? So we're only seeing what remains after passing through. So that should be the transmitted, not scattered, not absorbed. So this detector isn't perfectly, has a finite field of view, right? It can't be infinitely collimated in the direction it's looking. So, so there's a little bit of scattered light that does get detected. For the absorption tube, I kind of like this figure from the NASA protocol document on the measurements from after authored by Meg Estapa, but it's a nice diagram that shows exactly how this A side tube is working. So we've got the source coming in at this end, and then the walls of the tube are made of quartz, and the mismatch and refractive indices causes light that's scattered through angles less than 42 degrees from the incident to still be collected. The light, I'll trace one of the photon paths here. Coming in this way, it changes direction, bounces back out, changes direction again, and it's retained, right? So anything that's scattered through an angle larger than 42 degrees is not retained, right? So we're only catching some of the scattered light, but it's better than, you know, spectrophotometer doesn't really get any of it. And we'll get more on scattering tomorrow, but a lot of the scattering is sort of concentrated in the forward directions. So less of it is back scattered. So it's pretty good. So only light scattered through those steeper angles. And then attenuation has this black non-reflective walls and a narrow field of view detector. This is a photo from the ACS datasheet at Seabird. That's what the instrument actually looks like. You will get your hands on it this afternoon, so I don't need that. But and then, oh, this also isn't showing up super well. To have the computer in front of you, you can follow the DOI to that and get the actual figure. Yeah. 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 It's okay. Anyway, I think I've spoken all of the salient things, showed them to you on the simple diagrams on the last page, but later on we'll post this electronic version on the web and you can look at it on your screens if you'd like to look at that schematic. It's a nice one. So as I just was saying, absorption, some of the scattered light is lost and not detected on the A side. And so the absorption is overestimated, right? The sensor sees less light than it should based on what was actually absorbed. And attenuation is underestimated because some of the scattered light is collected, even though we don't want it to be by definition. The acceptance angle of the detector on the C side is something like close to 1 degree. And there are instruments out there that have a tighter acceptance angle, much less than 1 degree. And so you can really see the difference in the scattered light that is collected by the AC meter C side. So we have to do some correction. So to start off with, we'll define the measured absorption. E is scattering, C is attenuation. So the absorption, scattering, and attenuation measured spectra, we'll put the little subscript M in front of them. A plus B equals C. Math is E. So I'm going to talk you through just some of the correction methods that are used for this. So the figure I'm showing you here is from a paper by Rudiger Rutgers, which was nice just because I could like block out different bits of it and animate it in, but there's lots of figures out there that you can take a look at and get an estimate of, or get a visual on what's correct. So we're going to say A, without any subscripts, is the true absorption spectrum. And on this figure, it's the solid line. Okay, so that's the actual one, or close enough to true, measured in this study by putting suspension in the middle of an interval here. And then we want to, before we do any of these scattering corrections, we have to correct our absorption, our measured absorption spectra for temperature and salinity of water, right? Remove the water part and correct for any temperature and salinity offsets from the pure water estimate. So that's already done for this. So the little triangles here are the measured absorption. You can see clearly absorption is overestimated. It's too high. And so there's a few different ways that we can go about this. One assumption that we could make, and it's valid or more valid in a lot of like open ocean places. You can assume that the scattering in the near infrared part, or sorry, assume that the absorption in the near infrared part of the spectrum is 0, right? Because CDOM, non-algal particles, phytoplankton, all of them have absorption spectra that kind of tail off as you get into the near infrared. It's not always true, particularly in coastal regions. And this study was all coastal samples, and you will see that in the absorption section. So actually, you can see it here. The true absorption is non-zero in the infrared, but the first scattering method that we can try does assume that. So we take the calculated scattering, the difference between C and A, measured, and we use that to estimate the scattering correction. So we use epsilon as and that's also a function of wavelength. And assume that the true absorption is 0. Okay, so option 1 is called the flat scattering method, where we just assume that the scattered light that's lost is spectrally flat. You basically just remove the measured absorption at 715, or whatever your longest near infrared wavelength is, from the whole spectrum, and it just drops everything down by that offset. So that's what the black dots are. That's the flat correction. And all these corrections are from a oceanoptics conference paper by Ron Donovan back in 1980. Okay, so you can see that it does a pretty good job of correcting the absorbance in the blue, not so much for this sample, which was coastal in the near infrared. Option 2 is to assume, again, that absorption in the near infrared is 0, but that the epsilon is equal to a constant proportion of the measured scattering. So this allows that epsilon to vary spectrally. So if you calculate that, then you end up getting the open circles, right? In this case, it actually didn't work as well, partly because of this near infrared offset and also because of the scattering properties of particles. Okay, what if you don't want to assume that absorption in the near infrared is 0? So here's all of the samples, or I guess it's a set of examples of all of the samples from the Rutgers study. So there's, so all of them have the same symbols as on the last slide. And you can see that they have varying amounts of scattering in the near infrared. So like this one's pretty close, right? The true absorbance or absorption is pretty low in the near infrared, and the corrections do a little bit better job than, actually same thing here, than this one that I was showing you before, River Elbe, where there's a lot of near infrared absorption, and those corrections don't come as well. So if you don't want to make that assumption, then you can do a different empirical correction. It was proposed. So this is taking, again, samples in an integrated sphere and coming up with an empirical relationship between the absorption, true absorption, and the measured absorption. And then you can use that to correct your absorption measurement in the near infrared, and then proceed with the rest of the correction. You also, in this method, they also correct the attenuation coefficient for that under collection of, or the over collection of scattered light. Manuel has his hand up. They were using, okay. Yes. Yeah. 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 Right. No, I mean, you have to have an acceptance angle, but right. 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 I think in this correction in this paper, they used your measurements from like, but it was from one place. Yeah. Yeah, but it was totally an assumption. Yeah. Okay, so we say if you know. Yeah. Yeah. Yeah.
And the same thing, there's absorption, right? I mean, because I themselves don't have absorption. Red. So they're basically saying, I know that there's some fraction of absorption in here in the red. And it used to be 70%, that is correct. 70% of what is in here in the red is the rest scattering. Yeah, okay.
Yes. Right. But does the second one get used very often?
No,
or
still work to be done. And what you'll see when we measure things, we'll show you tomorrow, you'll see that there is absorption in here. And right before you find the sample, you can think about like, how are you going to quantify? Well, how did you guys here you can do it, but as it's slow, we'll show you it's a slow process to make those measurements. So you're going to have to think about how you do these corrections. It's not as straightforward. So this is what
it's one of the approaches that I think we ask in the lab tomorrow. We will ask you to try these different approaches. And so this is how this one came about. Yeah. 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 So anyway, there's too many animations. Never mind. But yeah, so the just Zonneveld based ones and all of them are going to be kind of options that you can test, but now you know where they all came from. So the last thing I want to talk about is a paper that was published a couple years ago that Colin is one of the co-authors on, and I think Ivana co-edited or edited. I think she was the associate editor for that. Yeah. Yeah. Anyway, yes, it's like many well-regarded people making these kinds of measurements got together with all the instruments that they had, or at least a subset of the replicate instruments that they had, and went to a complex coastal region in Florida and did an inner comparison of all of these different methods. So measuring total non-water absorption, CDOM absorption, particulate absorption, the phytoplankton, non-phytoplankton, cross-comparing them across transective stations with different properties to see if they could achieve absorption closure, right? To get everything to agree. And I've just pulled some panels from all from the same station, comparing some of these different methods here. I think the only method on here that we haven't talked about at all is one called Gerson's method, which is basically measuring the net irradiance, net scalar irradiance, and from that deriving the absorption coefficient. And we are not going to get to that, I think, till next week, maybe. So, but what I would like you to do is a little think, compare, share. So look at this table and the figures, talk to your neighbor, and just see if there's anything on here that you're like, what the heck is that? We didn't talk about that. I don't know what that is. I'm really confused. So that I can answer questions in case there's something we didn't get to. But ask yourself, could you read this paper and follow it? Because it's an excellent example of inner comparison. There's lots of methodological details. If you're interested in absorption measurements, it's a good one to read. So you have the vocabulary now to read this paper. So take a minute and talk with one or two neighbors and see what you think. Okay. Do you guys need a few more minutes or do everybody just got really quiet, so you're not fighting with me? So, among you and your groups that you were talking with, are there some things that are still muddy that you would like to revisit? Yes? What are they? No.
A non-water
Yes,
is all of these are
yes.
how
Measure, you measure total absorption,
Okay.
subtract water. Or you measure all the components, all the components except for water. Manual set. What else was muddy? Yeah.
I'm gonna get it.
All right. I'm gonna let Colin take that one.
And it was designed by a guy, the water animals. And then he turned over the design to Turner to implement it into an instrument. And I was funded to test that instrument as part of this program. And so I did. And it must have made the design of that instrument such that it wasn't what was in a lot of papers that we read by Fry and Gray. I could not replicate any of their measurements. And when I tested it against AC meters, SciCam, and I didn't find my own and there's not. And it has much power in front of me. And also implants. you read the paper, they are, it's a, that when you really have a diversity. Yeah, and it's no longer sold by Turner.
I went to look.
So, yeah, so it's just one of those like. But the page is like, oh, it brings you, it brings it.
Yeah.
Yeah, you're right.
Look at the blue dots.
What else?
Now, when the conversation. Oh, how should I know what that? This is out where we've got fiber optic to inject small sample through with light bounces. All the other side. Here, can I figure out how to go back to it? Not easily. I'm gonna have to go back to a lot of slides. But it's, I'll show you on here. Yeah, super, it's when you need a half meter or longer for the open oceans, yeah. Mega path. Yeah. Method is the one where you measure the irradiance for text. So you're looking at the planar irradiance down, planar irradiance up, taking their difference. It's called the net irradiance. And then you need to measure the scalar irradiance, which that's from upward irradiance, scalar irradiance, and downward scalar irradiance. And those two together, you can back out the absorption. So it's using, rather than measuring fixed sample volume and the light lost to absorption along that, you're measuring the light field underwater and making some assumptions about, like, we're integrating out the scattering basically with those measurements and just looking at the absorption. And we will, it's the only method that's in here that I'm like, we've not talked about this yet. It'll be better for you to hear it from Andrew probably next week. Yeah. Yeah, it's gonna get, we're gonna get there. So that's the one thing that it's okay if you read this next week. Okay. Other things? How much did the person that you were talking with help you figure out the things that you were muddy about still? That was a poorly phrased question. Did pairing up with a partner help you clarify a lot? Right? So let this be, so tonight you're gonna have a whole crap load of data, you're gonna have to synthesize it really fast and come up with some good explanations for what you're seeing. Use each other, talk to each other, right? This is a little tiny exercise, but you're gonna have bigger stuff to do very soon. Okay, Colin had something to say about this too.
We all begin with our history, and we all have some both samples and everything. And my point was, but each hour, and so when people work together, there was just a lot of conversation. Longer and longer. And I would say, you know what? There's something. It's not a part came up with a set of figures she thought demonstrated. We all commented on it. We all made contributions. I wrote the section on the garbage. but ultimately, we do that. It created a loop of us analysis. And so I think that it's really important to recognize that often biases, some of them are legitimate, a lot of experience, you know. But also biases in like things that we need to be able to trust. So by bringing in this postdoc, it was an excellent way for us all to check our. And for Scott, that is what we are. But it was awesome. I love working with her. She's great. She's not the opportunity. But I just got in your path and hold it there and think about it as we move forward. Maybe not quite making the work you've done the way you should. Volunteer, like, get over that. It's not enough fault. Or when you get to get a little bit further along, you're like, someone was. Okay, so it's a great example. Of the-
So just quickly back to the roadmap and what's going to happen in the rest of today, and then we can break for lunch. So we just finished the second absorption lecture this afternoon. Lab absorption technique, simplified situation. Option 1, remove the scattering. So we're just going to use filtered water samples, and you're going to split into 2 groups. Is somebody going to give an overview of this later? I don't want to replicate, but figured it as well. Okay. So you're going to split initially into 2 groups, and you'll spend half the time in each group and then swap. So I guess it's a hour and a half, 90 minutes each. So 90 minutes in each of these, and then you'll switch. So group 1 is going to spend half their time doing a simple Beer's law determination. So this is the 45 minutes, and then switch here. And then half their time learning to use the benchtop spectrophotometer to make dissolved absorption measurements or filtered water absorption measurements. So in that one, we will test the effect of temperature and salinity, the dependence of absorbance on the geometric path length or the cuvette path length. Also how to clean and care for cuvettes on the spectrophotometer, haven't used one before, and how to collect absorbance measurements relative to the appropriate reference solution. All this against whatever your reference is. On the other side, the group that's using AC meters, you'll learn how to operate the instrument, test the effect of temperature and salinity and path length, and also how to clean an AC meter, how to calibrate it, how to get good pure water readings, what are appropriate uncertainties, and then how to correct for the temperature and salinity effects. Okay. So this is the structure of the lab and generally what you'll be doing. And then what you're going to do is take all of the measurements that you collect and use them together as a group, synthesize them to answer 4 broad questions. And these are all of this is in the lab handout, right? Lab handout. We have those that you'll get in the lab this afternoon. But how does the absorption spectrum of purified water vary with temperature, with salinity? How does Beer's law come out of these measurements? You'll add dye to a fixed path length tank. And then how does the geometric path length impact the method absorbance and the derived absorption relation? So these are all things that you guys will be figuring out with your data from lab today. You'll need to work it up tonight. You can tell us the answers to all these questions, your data tomorrow morning, starting the day. Okay. Oh, right. In lab tomorrow, we'll kind of tag on to some of the things I was talking about during this lecture. So we'll get into particulate absorption measurements with filter pads. We'll do the partitioning into phytoplankton pigments and non-pigment, non-algal particles, and then making AC meter measurements with scatterers, so doing all the scattering corrections. So that's our roadmap, and that is all I have. You guys have any questions about the roadmap? Okay, let's go have, yes, a question. That was in the last. Okay. They didn't ask about that when I showed them this.